Hello. Today I'm gonna design a flash card for the N64, and I have close to zero knowledge about the Nintendo 64, so it's gonna be a learning experience. And yeah, let's see how many mistakes I'll make today. But hopefully I'll get something done by the end of the day. We'll see. So is the audio okay? Can you hear me? And feel free to correct me if anything I say is wrong and so on in the chat. I welcome feedback, any kind. So that's totally fine. So I guess we can start off by looking at existing projects just to get an idea of what's out there already. And yeah, n64.dev seems to be a very good starting point for resources. And yeah, I can make the text a little bit bigger. So the 64 drive seems to be like the state-of-the-art flash card out there. It's using an Altera Cyclone 4 and I think DDR2 memory. Obviously, a lot of time has been spent designing this and iterating and so on. Yeah, it looks nice. But it seems to be unavailable for purchase right now, at least. Maybe it's because of the yeah, lots of pending orders and stuff, and the whole chip disaster the last year or so. But yeah, it seems to be a really nice project. Then there's a bunch of others, a few open source ones. So yeah, let's take a look at those. So the Wurzelkarte, or however you pronounce it, seems to be a very nice project as well. Here we have a Lattice, Mako 2 FPGA, I think, using some SDRAM and yeah, some flash as well. And the whole design is open source, so that's perfect. We could, for example, use the PCB layout as a starting point, since all of the all of the dimensions are already sorted out, and I think this project has also been tested, so I don't have to worry about being able to fit the cartridge and so on. So that's great. Then there are two others. This one seems to be a little bit simpler, which is nice, keeping things simple and clean. And here I think it's a CPLD instead of an FPGA. And it's, as far as I understand it, yeah, it interfaces with the SDRAM. And then I'm not really sure how the SDRAM is being loaded, but I haven't spent that much time looking at this. Anyway, it's also open source, done in KiCad or KiCad, which is great. Here the PCB seems to be a little bit more simple, which is nice as well, keeping things simple. But I think the other one here will fit in an actual cartridge, which is nice if you want to, mount it inside of one of those. And then there's one more, this one, Summercart 64, which seems to be a very nice project as well. Here you can see the dimensions seem to be well designed and so on. However, I think this one is done in Eagle. Yeah. So yeah, I'm using KiCad, so it will be a little bit of a pain to import that the PCB layout, but doable, I guess. Yeah, and it seems to be tested as well, and which is great. And here the design seems to be an Altera Max 10, some SDRAM, FPGA chip, and then an SD card. So I guess the ROMs and so on are loaded from the SD card into the RAM, and then yeah, the signals are routed, and the RAM accesses are being done and so on by the FPGA. Kind of simple design. Actually everything is like there's no BGA, which is nice for hand assembly. Nice project, definitely. So then one might ask, why am I doing yet another one? Well, it's just a learning experience, and I'm kind of bored right now, so I need a project. So yeah, I just want to do something, and so I've been using the ECP5 FPGA a lot. I like it. There's open source toolchain for it for the whole flow from Verilog down to the bitstream, so that's nice. And I already done a few boards with ECP5, so I'm familiar with the FPGA side of things. So yeah. Yeah. So the idea is to basically try to port over the PCB layout from this project, because it's KiCad, so it shouldn't be too hard. And then just remove all of the components and basically remove all the redundant stuff from my old board and integrate that into this PCB basically. And while doing that, I'll also try to expose some extra connectors and stuff, because it could be fun to write some homebrew that is able to do more than just reading from a ROM. So basically that you can connect to the outside world through the FPGA by accessing addresses that are not in the ROM. So for example, you could do basically anything. Memory map, whatever. Maybe Ethernet on your N64 or Wi-Fi or whatever. So I think I'll put some PMODs. PMODs are nice because they are 8 IOs and 3 volt and ground, 3.3 volt and ground. So it's a good expansion connector for simple IO. Like it doesn't support very high speed signals, but I've run HDMI over it, so it's like, yeah, you shouldn't use high speed signals, but it's definitely possible to do so anyway. Yeah, so that's basically the idea. So yeah, to recap, try to take this PCB, strip all of the components, integrate the ECP5 on it instead, and yeah, that's about it. So before we continue, I guess we should try to make a high-level overview of what we are trying to achieve. So yeah, for some reason I made everything on a one sheet here, which makes it a little bit harder to make another one. Well, I'm gonna do so anyway. So I'm a little bit rusty with the KiCad. Last time I used KiCad was like a full year ago, so I might be a little bit slow. Yeah, I think this is what I want to do. So I'm just gonna create a subsheet called overview. Yeah, there we go. And yeah, so, and if anyone in chat could just write that you can hear me and so on, that would be nice, because yeah, it's a little bit hard to test. But yeah, also just write anything if you hear that I'm saying something stupid or wrong, and correct me. That's totally fine to do. Yeah, okay. So the idea is, maybe I should just use text. So if we just have a look at this one. So here you have the cartridge, and all of the signals are basically going into the FPGA. And because it's 3.3 volt, we don't have to worry about level shifting and so on. It's just going to work, which is perfect. There is no series termination here. Like the signals go directly from the cartridge connector straight into the chip, which might be fine, but I think, if I'm not mistaken, yeah, here they're using 47 ohm series resistors, which I'm not sure if it's strictly needed, but it might be nice to have. I mean, they're basically free, and I already have a bunch of those because I used them in this project here. Yeah. All right. Yeah, so another thing that I'm gonna have to think about is that because of the current situation with electronic parts, it's kind of a big pain to buy standard components right now. I'm gonna try to reuse components that I already have on this board because I have parts for like 5-6 boards of this, which means that as long as I keep to this BOM, this bill of material, I should be fine. And here I have a bunch of stuff that is nice to have. Yeah, so that should be okay. Yeah, I wanted to switch out the. Actually, this one is a weak one. Yeah, I was thinking about the 2.5 volt rail. Because here I'm using quite nice, not nice, but quite beefy DC-DC regulators that can provide a lot of current, which I will need for the 3.3 and 1.2 volt rail. But for the 2.5, I don't really need that. But yeah, I'm just using this tiny. I think it's a 200 milliamp. I think I have it in the schematic. How do you do this again? Yeah, here we go. Yeah, right. 200 milliamp regulator here. So that's fine. All right. So I guess what I should do is to, yeah, let's do the overview. So we have the cartridge, and we have the FPGA, and then we have SDRAM. Oh, hey, nice to see you. Welcome to the stream, everyone. All right, so I'm just doing some overview here, just to get like an idea of what we're trying to build. So we're gonna need some standard stuff, some SPI flash for the FPGA, and we probably want to have some USB connection as well. So I haven't really thought about this too much. Quite honestly, this whole project is a sudden desire to make something for the N64. And I have 2 weeks of vacation, so I'm trying to speedrun this. But usually that ends up with bad design decisions, so that's why I'm streaming it. So if I'm doing something really, really stupid, someone can hopefully say stop. So anyway, the basic idea is to be able to interface with the cartridge through an FPGA. And then by connecting SDRAM, I should be able to make a cartridge emulator quite easily. And then we have the standard SPI flash to boot up the FPGA. And are they 3.3 volts? Yes, they are, which is really, really nice. So there's no need for level shifting. I mean, I was just going through some existing projects, and I think the most promising KiCad project is this one, which is basically an FPGA, SDRAM, some flash, USB, FTDI, and that's about it. But yeah, since I like the ECP5, I want to make a board with that, and I also have the ECP5 at home, so I'll be able to build the board. And I should also have some SDRAM laying around. So yeah, so the idea is to basically borrow this open source PCB design for the what's it called again? Yeah, for the actual PCB, and then put basically the ECP5 project on there. SD card for mass storage or images, or built-in eMMC or NAND flash? Yeah, so that's a good question. So there was this other project here, which is using SD card for loading stuff into the SDRAM. And I'm thinking that this is probably a good design, but for sort of fast, should I say? I want to be able to get stuff running quite quickly, so maybe I'll have to struggle a little bit with the SD card integration. So I'll probably put some old school SPI flash on there as well, because that is so easy to integrate. So that's like this is going to be an experiment anyway, and the first revision will have more test points and maybe more connectors than you probably should have, and so on. So I think I'll just put a little bit too much on this board, and then we can remove it in the future. And I was thinking about using high-speed DDR3 and so on, but that's bad for multiple reasons. Like, first of all, there's the whole latency issue, and then there's also the PCB routing issue with the length matching and so on, which I don't have to do here, at least not in the same critical way that you need to do it with the DDR. Yeah, so the question is here, USB stuff, how do I want to do that? Like, I want to keep things simple so that I can basically finish this today. So I'm not really sure about this part. So on the Pergola board, I used this IMX RT microcontroller, and I'm not gonna do that now because that is big and unnecessary. It's a little bit unnecessary. And I want to keep firmware as close to 0 as possible. Like I could do the whole USB inside of the FPGA and reuse the whole your bootloader basically, Sylvan, and that way I will save a lot of time and so on. To compensate for DDR3 latency, you have to clock it fast, which is annoying. Yeah, I was thinking about exactly that. So, like, yeah, technically, I could run the ECP5 at a high speed and and do just that. So it seems that the latency, I might have to handle stuff at 80-ish megahertz. So apparently, when you boot up a ROM, you're telling the host a little bit about how fast stuff is going and so on. And so it seems to be a little bit dynamic, which means that I guess I could clock it down if I want to, but yeah, that's just a mess. So I'm gonna stick with SDRAM because that is sort of a proven way to do it. So yeah, I guess I'm just gonna rip out stuff. So this part is easy. I just put a SDRAM and connect it. This part is also easy, and this part is also more or less easy. I could put some serious resistors. Like so. And then we need SD card. Yeah, so the question is about USB. Yeah, and I guess putting a USB 2 PHY here feels overkill, but it's like if I reuse the stuff from Luna, putting a USB 2 PHY here so I can do high speed, high USB 2 high speed stuff into the SDRAM. Like you connect the USB to your computer and you just download stuff to the SDRAM quickly. Because otherwise we're having, what's it called again? Full speed USB, 12 megabit per second, which, I mean, should be fine, quite honestly. So I'm gonna have UART connector and JTAG connector. Yeah, and of course we need power. That's always a little bit annoying, but so I was thinking about doing it in two ways. Should have USB power and cartridge power, and then maybe a MOSFET to mix it. I don't know. Does that make sense? So that before you boot it, you could connect with USB, and then prepare the SDRAM from your PC, for example. And after that, you boot the N64. I don't know. Maybe that's just annoying. For the first revision, maybe I shouldn't really think too much about that. Because this is going to be a developer card anyway. This is a detail. We can look at that later. But yeah, I think this is basically what we want to do. Does that make sense? Oh yeah, we need a clock as well. So where should I put that? Yeah, whatever. So we get the frequency. So right, I have a 16 megahertz clock here since before. I think that should be fine. I will need to PLL it to the appropriate frequency and so on. But yeah, this is the high level overview of what we want to do. Just thinking if I should put a microcontroller here or not. Like, it's always nice to just plug in USB and off you go, but it also adds complexity and another BOM line, which right now is not very fun. I mean, just buying an STM32 standard thing today is almost impossible. So I think I'm gonna skip that. All right. Anything more? Right. We need connectors. Oh, wrong button. We're gonna need. So yeah, I think this got a little bit messy. Okay, so this simple board in my head turns out to not be that simple, but let's see if it makes sense. Yeah. So for the SD card, I'm gonna have to look at someone else's design. I almost know nothing about SD cards, but on this one, it looks like there's no level shifting at all. It just connects straight into the FPGA, and yeah. So I'm gonna try to use 3.3 volts throughout the whole design. Yeah, so for storage, let's see here. So I'm thinking of just putting a bog standard SPI flash for the FPGA configuration. I don't know if I'm trying to figure out if I should put some extra flash. Can it just use the SD card? Yeah, definitely. That is the idea. But in order to get there, I'm gonna need to I need to get there. So right now I'm starting from 0. So just having something that is easy to use for me while developing is also nice. But I guess the SPI flash, I don't know. I'll just do it like this. I'll put 2 SPI flashes on there, and then because SPI flash is so easy to use, yeah, that will be a good start. But yeah, in the future, or like during development, I'll probably write code to actually interface with the micro SD card. But that is, I expect this to not be as simple as just writing a few lines of code and off you go. It will probably be a little bit more complicated. So instead of the FPGA, I'll probably have a soft core RISC-V CPU that can, yeah, implement file system and so on, so we can read off files from an SD card. But can the FPGA configure from an SD card? I guess not. No, not without bootloader. So what we could do, that is like that is more for a user, I guess. That is to on the SPI flash, put the bootloader so that the FPGA boots up and knows how to read stuff from the SD card. I mean, that is definitely possible to implement, but that is not where I'm going to start. So that is further down in the roadmap, I suppose. And who knows, maybe I'll grow tired in a few weeks and it will be another abandoned project, but I hope to learn something from this. So I don't want to over design it, keep things lean. So all of these are just connectors. So So the USB goes straight into the FPGA. UART, it's just 2 pins. JTAG, same. And then some extra connectors. So exactly how much and so on, I don't know. Let's say 2 PMOD connectors. That gives you 16 IOs. Could be fun. And then for the power, yeah, that's, I don't know. Maybe I'll just have a jumper. Because, yeah, that's true. Just do it like that. So you can switch between USB and card powered. Then the oscillator, yeah, nothing strange. Micro SD card, that's also a connector actually. So all of these are just connectors. So these are just a footprint and connect wires, nothing strange. And then the SPI flash and SDRAM, that's easy. You just connect them. Yeah, and this is also quite easy. So I mean, the whole system it's nothing complicated. It would get complicated if we had like a microcontroller and stuff. So I'm just not gonna do that. Yeah, I'm not gonna do that to keep things simple. Okay, so let's rip out stuff. So the schematic you're seeing here, it might look scary and big, but that is for this pergola board that I made like 2 years ago. And we're gonna basically remove the microcontroller part and right, what's it called again? PSRAM, pseudo SRAM. We're gonna rip those out too because I don't think it's gonna be useful since we have the SDRAM. Then the buttons, yeah, we can have buttons if we want. It's nothing strange. Some LEDs are nice to have. Probably don't need all of them. And then all of this configuration mess we can just remove. We can keep the ECP5 in the JTAG or a SPI mode, so that it when it boots, it will pull configuration from the SPI flash. And yeah, can remove quite a lot. Yeah. So let's do that. Okay. So regarding power, we need our 1.11 volt that is required for the FPGA. And yeah, this is a DC-DC converter with an external inductor. This is a tested design, so I've already done stuff with this, and I know that it works, and I already have the parts, so that's good. That means that I can build this. Here we have the 2.5 volt rail. There's basically no load on that, but it needs to be there. And then we have the 3.3 volt, which is yeah, what we're gonna use for I/O. And already here we can rip out some stuff. So this is a power good signal generator. I forgot the name of it, but anyway, it will. Yeah, it's an open drain signal when the voltage is good, but we don't technically need that, so I will just rip it out. And we can remove this one as well. And then here we have the USB-C connector, where we need the 5.1 kilo ohm. That is part of the USB standard. Yeah, not much we can change here. This part we can remove. So this is the microcontroller on the board, which we don't need anymore. So I'm just gonna kill it. and yeah, all of this. Then this is for the configuration of the IMX. We don't need that either. Here we have the SPI RAM, which we don't need. Just remove it. Actually, now that I think about it, we can remove it. Because we might want to have an extra flash. Then here we have the boot flash for the FPGA. So this is already connected to the appropriate signals. And we can remove the IMX, because this was a shared design where the flash was shared between the FPGA and microcontroller. And that turned out to be a very bad mistake. So I'm not going to do that again. Yeah, all of these are pull-ups, which I think according to the datasheet are needed in practice. Yeah, you might not have to place all of them, but yeah, it's good to have the footprints anyway. Here is the 16 megahertz clock or oscillator. No, this is the oscillator, right? So this generates a pulse of 16 megahertz. Yeah, when you design FPGAs, it's kind of important to not confuse a clock with or like a crystal with a oscillator, because crystal doesn't do much if you don't have a driver for it. All right, and here we have the PMOD mess. Yeah, I guess I can keep one or two. I'll keep two PMODs. Then we can connect the signals in a way that makes sense. Yeah, I don't think we need the 5-volt. I mean, we can keep the 5-volt. Yeah, doesn't hurt. It's basically free. Okay, so here we have JTAG connector, SWD. SWD we don't need because that is for the microcontroller. All right, then we can rip out the signals that are for the IMX. Yeah, basically all of this. PMOD 1 and 2. PMOD 5. Yeah, the RAM goes away. Okay. Let's have a look over here. JTAG, right. Yeah, we need those pulls. Otherwise, we might get spurious stuff on the JTAG. We don't want that. Yeah. Right, so this stuff we want to configure once. Right, so we want to be master SPI, I think. That is sort of the standard way. Yeah, we don't. Need this now. So I'm just gonna hardwire these, I think. This is always like these signals are kind of buried under the FPGA. So if you don't pull them out, it's gonna be a pain. So let me just show you. Oof, it was a while ago since I looked at this board. I think it's these. Yeah, exactly. FPGA configure. So there we go. So yeah, there we have one signal. It's 3 columns in. And then we have so P10 and N10 and R10. So it's these 3 signals. So they are kind of a pain to pull out if you sort of hardwire them. I'd recommend wiring the SPI clock to a normal I/O pin in addition. Oh yeah, because I remember why. That's a good suggestion. Because in order to drive the SPI clock signal, this one, you need to instantiate a special block. You cannot just do normal I/O stuff. I remember that. So N10. Oh, did I crash it? Where do we have N10? There. Okay. So let's say M10 perhaps. Perfect. Just really close here. So how do you copy stuff again? Okay. Now I'm supposed to find M10. I really feel rusty in KiCad. It was a while ago. I think maybe here somewhere. Should be a signal that I've used before. I guess I'm just a little bit blind. M14. That's a little bit annoying that you cannot search for the number or the pin number. But yeah, M10. Where was it again? Well, we'll get back to that. I'll find it sometime soon. Where are you from? Sweden. So yeah, if my dialect is a little bit weird, that's why. Okay. It should be here somewhere. M11. Well, yeah. Let's fix that later. Okay, so now we have pulled out all of the stuff we don't need. So about the LEDs, maybe we don't need an RGB LED. That's a little bit overkill. Can remove those. And also, they are kind of annoying to mount. So, thanks for the follow. How many LEDs do I need? 4 status LEDs or 8? Well, I can remove them if I don't need to. So it's always good with some LEDs. The nice thing with having 8 LEDs is that you can sort of write the full byte on there. That's kind of convenient. All right, so if I now press the magic button, a lot of stuff disappeared. So that's kind of nice. This is way easier to build. The previous one was a little bit annoying. And also I don't have any parts on the backside because that's, or actually I do. Sorry for that. But it's only some capacitors. So yeah. So I guess, yeah, we don't have to look at the PCB right now. Let's finish the design first. So the JTAG connector, we have that here. And then we have the, what was it again? We want the UART connector. The question is, what kind of connector do we want for this? I guess I can just take another one like this. Or it can be a 1x03 perhaps. Like this. A separate UART one. And we just right, L for label. So I guess technically I can just use a P mod for this, but it's kind of nice to have a dedicated UART on the board. I really forgot the hotkeys. Damn, it's annoying. Remember that there's a way to drag run components with the net following. I completely forgot what that is. If anyone in chat knows, I'll yeah, just let me know. Okay, so let's call this con UART. Right. So you can sort of yeah, let's skip the cart power, or I don't know. I don't know what the I haven't really checked what kind of power we have. We have 12 volt, which is, yeah, annoying. VCC is probably 3.3 volt. I don't know. If anyone in chat knows the voltage of the N64 VCC rail, yeah, just let me know. But I believe I would expect it to be 3.3 volt. I think there was some information about this somewhere. Where did I find that? Here, I think. Oh. Or perhaps just says VCC, but yeah, I guess that is 3.3 volt. And yeah, I don't really know if that is a good idea to sync current and not just use it for voltage, what's it called again? Reference. But if it's actually 3.3 volt, then we could skip out the whole 3.3 rail, but I don't think that is a good idea. But it would save some space. I mean, that is this one. But we want to be able to use the USB anyway. And having it wired like this, you're able to connect to the cart without it being connected to the N64. So I think I'm just gonna keep it this way. Right, so this one we don't need. This is just a user switch. I think this is connected to the FPGA as well. Yeah, here we go. So let's keep that. But you also want the cartridge to work without USB plug-in, right? Yeah, so that is definitely an issue. So I was thinking of no, I'm yeah. Let's not optimize too much about space. So yeah, if things take space, that's fine. But yeah, I was thinking of having a MOSFET that can choose between USB power and N64 power. So I was curious about the actual voltage that I'm like. Am I allowed to sync current from the VCC? Is that fine to do? And is this 3.3 volt? And if so, then I could use this as sort of a main rail. If not, then I will need to use the 12 volt, which is here. Yeah, it's not even connected on this project. Well, probably some current, not sure how much. Yeah, so I expect this to use a few hundred milliamps, I guess. It's really hard to say, but the RAM will probably take some power. Yeah. Are there specs for what kind of power you get out of the N64? I don't know. Um, and it's a little bit scary to. Yeah, exactly. I don't want to click on too many links here on the stream because, yeah, there are some links that should be unclicked, I suppose. But if anyone happened to know, yeah. So in any case, for the very first revision, maybe we can just have a jumper. And basically, this is the main 3.3. Yeah, okay. So looking at the power net, the way I did it is that I have VBus as sort of the main voltage rail that goes to all of the other regulators. So if I want to feed the VCC from the N64 to this rail, I would also have to feed that rail to these. So I could rewire this and have like all of these taking the 3.3 volt as a source. So basically using this as a source for the other. But then we get like in the USB case, we get the DC-DC and then another DC-DC, which I suppose is fine. I don't know. I don't know. Silvan, what do you think? Should I have the DC-DCs in a cascade? Any power sequencing requirement for the SP5? Yeah, so technically yes, but in practice, not really. I suppose you don't really have all that much choice in the matter anyway. Either you get enough or you don't. You mean regarding to the power? Yeah, but like, let's say, for example, that you can only sync 100 milliamp on the VCC rail. Yeah, you could source from the 12 volt rail in that case. But yeah, I don't know. Can those DC-DC take 12 volt as input? No, so I don't. It was a while ago, but they are these kind of small and cheap regulators. So let me just look up the. There should be a datasheet here somewhere. Oh, oh, okay. Hmm. Um, you know, 18 volt doesn't sound that bad. I did not expect them to accept that much voltage because they are really tiny. Uh, hmm. That's, I did not expect that. Okay, yeah, thanks. Um, hmm. Okay. I guess the problem is then this small linear regulator, but that is so insignificant, so I can put that off on the 3.3 rail. I'm actually gonna do that now. So I'll remove this and do like this. I think. Let's just check the datasheet for this one. Oh. Does this mean that you cannot source this part anymore? Oh, crap. But I have a few ones left. Oh, here we go. 27,000 in stock. Okay. Wow, look at this. We're in the middle of the component crisis, and you can buy these for $0.03. And they have a bunch of them in stock. Perfect. So anyway, let's have a look at the datasheet. Okay, while that is loading, let's see if there are no information. Ah, yeah, one of those. Yeah, okay, so it seems that it can take up to 5 volts, which is, yeah, it should be fine to connect it like this. I was interested in sort of how much voltage it drops. I've actually looked into designing something like this for GameCube a while. Do you have a source for the physical connector that's better than just sacrificing an old card? No, sorry, first of all, I don't know anything about GameCube yet. And yeah, no, sorry, I don't know. I literally just hopped into this project without knowing anything. So we're all learning together. And regarding GameCube, you mean for the N64? Okay, okay. Well, I saw some 3D prints. Or you mean the physical connector? So as far as I understand it, you should be able to just use a PCB edge, and if you want to do a proper project, make sure to order it with the ENIG and what's it called again? Yeah, when you get those fancy edges. Gold fingers, yeah, that is what you want. So then you get those 45 degrees or something edge connectors. Or it's actually this one. So you want to have both of these checked. So you get both the hard gold and the chamfered edge. Because if you have a 90-degree edge, you sort of destroy the connector on the N64. Yeah. Okay, so now we have worked out this part. So the question is now, what do we do about this? Yeah, right. We just confirmed that this one can take 18 volt. So let's rename this net. Let's move this and call this V supply. You can also just use a file to bevel the edge yourself. Yeah, that's that's a good trick. Definitely. And I guess honestly, this like the first revision I'm gonna order, I'm gonna go with that suggestion actually, because I'm kind of on a time limit here. I want to be able to get the boards quite quickly, and also if you have fancy boards, it takes more time. Okay, so let's design the voltage thing. So, right, it's called power. Oh. Right, so we had a 12 volt, right? So these are the either from the USB or from the cartridge connector. So, and then we have the label called, I'm just gonna copy it, V supply. So, oh, now I already removed the, no, I can take this one. Nice. I have these jumpers already. So this is basically what you want to do. So something like this. But now this symbol is a little bit confusing. You don't want to have these connected. Maybe I'll just add another one. Okay, so a little bit confusing. So these actually mean that it's open. So yeah, then it's done. So I was thinking about having some fancy MOSFET thing here, but nah, let's not do that. So either it's USB powered or cartridge powered. And I think, yeah, let's move that a little bit. You might need to review your DC-DC design since it will be running at different operating points. Yeah, that's true. Oh, right. The caps on the high side needs to be 12 volt compatible. But other than that, I believe that it should be fine. Keep it simple. Yeah. Honestly, yes. For the first revision, let's just do that. And yeah. All right. Regarding this, we can look at the datasheet together. I don't think, I mean, the reference design is, I mean, they have one bulk cap on the high side. And yeah, okay, right, that is not really the reference design. Let's go down to the reference. Should be here somewhere. I think it's literally, it is just this. It's nothing more fancy than cap on the high side, and then the throwback or whatever it's called, inductor, and a cap. So it's this one here. Voltage divider and the feedback. Optionally, small cap there, this one here. And then bulk caps on the output. Come to think of it, do you need to deal with the whole CIC problem? Yeah, so let's talk about that soon. Yeah, MLCC also suck at DC biasing. I had to go for 50 volt radar caps for a C64 design using the 12 volt rail just because of voltage derating. Oh, that is interesting. Okay. Yeah, I almost never do stuff in 12 volt that is outside of my comfort zone. 5 volt is high enough. uh, hmm. Okay, so I guess I should be careful about these caps then. Make sure they are properly rated, I guess. But that should be it, because they're, if we look at this net, the pink stuff on the screen right now, that is literally only the jumper and the inputs to these two DC-DCs. So I think this should be fine, but it's a good to keep in mind that the 100 nano is should be a proper 100 nano and not just a random. Because at the hackerspace we usually keep 100 nano. Yeah, we have these standard values, sort of easily accessible, but they are sort of rated for 5 volt or something. I don't know. Definitely not 12 volt or 40 or whatever. Anyway, thanks for the heads up. So regarding the CIC problem, I was thinking about a few different solutions for that. So yeah, that's a good thing you told me about that. So we could put a header or connector for the CIC chip, which could then be, let's see here. I think this project is the most promising one. It's some firmware for a tiny, and they are small, cheap, right? They have like 8 pins or something. Yeah, right, 8 pins, and seem to be easy to program and so on. So that is one solution. I'll just take that finished project. I don't need to think. It will just work. That is one solution. Or I connect the pins into the FPGA, and then I run a soft CPU and port the code to run on that. Now, for some reason, I think it's written in assembly, probably in order for it to fit on that tiny, but I'm sure there's probably some open code. I think actually for the other FPGA project, let's see here, this one, I think there was some code regarding that too. Yeah. So here is some firmware for it. So here the CIC chip is implemented as a soft CPU with firmware running on the FPGA. And I was thinking of, oh god, a tiny soft course. Wow. Oh, that's cool. I respect that, but yeah, I want to understand what I'm doing. So I was thinking of just taking bog standard C code and using perhaps serve or Pico RV32 or something. Something that doesn't use too much LUTs, because I think the speed is really, really slow. It's like a couple of megahertz that the bus is running at. But sure, the whole crypto process or hashing or whatever it is, I haven't looked at the details. Yeah, need to be finished in time, of course. But yeah, I definitely think it would be fun to put this inside of the FPGA, but I'll also put a footprint so that if I want to give up, I can just put a chip there and it will be done. Or at least have the wires exposed so that I can give up. Or actually, you could also do the super old school mod that I read about, where you use another cart for the CIC stuff in order to boot yours. That's kind of creative. I like it. But yeah, that's I don't think I'm gonna need to do that. But I'm gonna, yeah, let's expose those pins. All right, I think we've done some good progress. So what's left? So maybe I should. So all of this is done. We need the micro SD card, right? So micro SD card. Let's add that. So perfect. I mean, KiCad standard library. Thank you. Perfect. Yeah, this is nice. So yeah, we need to connect it, but let's think about that later, because we want to choose good good IOs on the FPGA, so we don't need to route all over the board. I guess we can connect some simple signals. So yeah, again, I don't really know anything about SD cards. VDD, should that be 3.3 volt, perhaps? I need to, okay, gotta run. I'll check back later if you're still online. Okay, cool, thanks. So yeah, I think I'll stream until I'm too tired, basically. So hopefully we're gonna do some PCB layouts later on. So, but yeah, we'll see how far we get. Yeah, so we need to hook this up. All right. Yeah, gonna need to finish that. So now we have this, that. Okay, we're gonna need an extra SPI flash. Yeah, let's do that. And I'm just gonna copy this whole thing. I have to check the hotkeys. G, right. Yeah, there we go. Micro SD uses 3.3. Yeah, okay, perfect. I don't know. It's kind of overkill with all of those pull-ups, but yeah, whatever. Okay. Cool. Now we need the SDRAM, right? So I think this is a standard footprint or schematic symbol in KiCad as well. Let's see if I can find it. Here we have it. Perfect. Okay, this is interesting. So this card is battery backed, and they make sure to only let the battery go to the RAM and nothing else. By having it wired like this, the voltage from the battery goes through this diode, but not through this diode. So it doesn't backpower the 3.3 rail. So that's kind of nice. I could add this. Like, I'm not expecting this to be like a proper. It's kind of hard. Like what I'm designing here is like an experiment board for myself, but at the same time, it's like stupid not to do a nice design, I suppose. Okay, what do they do here? They have 2 flashes, which is nice. That way you can sort of address the full byte per clock cycle. Yeah. That's kind of interesting though. They share the net for the I/O signals. That's kind of strange. Okay. So I would assume that they have enough I/O pins. Oh well. I'm gonna have separate I/O pins for the 2 flashes because that way they are completely separate entities and can be accessing different data and so on, or get double the throughput. So it's up to you. All right. Yeah, we're gonna need to hook up a lot of signals though. That's gonna be quite a lot of work because the signals are usually like you don't want to just pick any random signal. You want them to be physically relevant. So yeah, that's gonna be an interesting one for sure. So I think we're gonna make this and do this in like 2 steps. First, we import the board layout from the other project, and then we can sort of lay out the signals so they make sense. That is the M10. I was looking for this pin. So I guess that is a bad pin. I should use N11 instead. Or hmm. let's do this one more time. Yeah, this one. N9. So it's this one. So I would ideally connect this one to like an adjacent pin. I'm not really sure which. Maybe M9. Yeah. No, that's also bad. Or actually, that might. No. It's really scary, or you need to be careful when you hook up these sort of configuration signals because most of the IOs, like this one for example, just a random IO, that is literally just like a GPIO, nothing strange. But if you're unlucky, it's a multi-function one. Oh yeah, thanks. SRAM. So yeah. Right. So this was a little bit interesting. So let's see here. This project, the Karte, seemed to use this one, the 62WV, which is an, like you say, SRAM. But the other project that I was looking at is using SDRAM. So I guess if you look at this table here, you can sort of figure out if it's good enough. So at 200 megahertz, latency 3, I guess this will be good enough. Let's see here. So the issue is basically from the time that we get the address until the time that we need to provide data. So as I understand it, this is configurable and different between games and different between the SRAM mapped memory and the ROM mapped memory. So for the normal ROM stuff, you usually get like some headroom to do the memory access. So in this case, we get the full microsecond. SRAM should be easier to drive. Oh, really? Oh, yeah. So it is really just address and data. That is, of course, very convenient. Because I was thinking of using perhaps Lattice, the light DRAM controller for the SDRAM, and then yeah, sort of use that to do the whole access. But maybe that is a bit convoluted. SRAM is of course nice, but I think the issue then is that the size of the SRAM is a little bit limiting. So here we get 64. Let's see here. My math is a little bit rusty. So yeah, 2 megabyte. 2 megabyte. So how much is 2 megabyte? That is unfortunately not a lot. A lot of games seem to be in the 4+ megabyte range. And for homebrew, I would like to be able to have like bigger stuff. I don't know. Like I like the simplicity. Like it's simple to hook up. It's just address and data. But yeah. Can we do a ping test? I wonder if the chat or stream is a little bit laggy. Like if I say ping and someone just writes pong, and I can reply when I see the pong. So let's go ping. Let's see how long it takes. Pong. Okay, that's not that bad actually. Thanks. Okay, anyway, so we have 2 megabytes here. Yeah, there I got the second pong. Okay. Yeah, it seems like the buffering is a little bit different, and also depending on where you are physically, I think, or geographically. So anyway, here we get 2 megabytes, which is cool, but I think the other one, this one, it was how much is that again? 64 megabyte. That's a lot, right? I don't think any game uses that much, and that would enable me to put like some pretty serious homebrew. Yeah, it adds latency. Yeah, definitely. But like if we, I've actually never written a SDRAM controller from scratch. I don't like understand exactly what this means, but if we run at 200 megahertz, or if we make it even simpler, if we run at 100 megahertz, uh, that means that it's 10 nanoseconds between each command, right? And then if the latency is 2 or 3, that means that it's the distance between, or the time between, or the number of clock cycles between the issuing of the fetch to the actual data is ready. So does this mean that it's only 2 cycles? And then, so that would mean 20 nanoseconds, right? Maybe plus 1 extra. If you know of a good resource about SDRAM, how it works, like a good overview, like I'm sure the data sheet explains this somewhere. You have this part. Oh, here's a auto refresh, self refresh. Oh, here we go. Command, nope, data out. Okay. So this image is like really interesting. So it simply means that if the CAS latency is 2, you simply get the data 2 cycles later. So if your clock frequency is 100 megahertz, then you have 10 nanoseconds between each clock. So, which means that you get a 20 nanosecond latency, which should definitely be fast enough. And then maybe we need to spend 1 extra cycle to actually read the data and output the data, but I would expect it to be like a mux where you connect the data straight out to the cartridge pins during that period. But maybe we need to register it, and then we get 1 extra cycle. Okay, and if CAS latency is 3, maybe that means that we can then run it at a higher frequency. So here we have at latency 2, we get 100 megahertz, latency 3, we get 200 megahertz. So that's, which means that here we get actually faster. Like the latency will be lower at 200 megahertz. But yeah, I think honestly, if we run it at 100 megahertz, it will be good enough. So I'm actually gonna. So I'm thinking if the pins are compatible, because they might be. Thanks. I will check that link. Okay, let's learn together. Right, we don't need this. We will only read or write to it. We won't. I mean, we will never have to read and write at the same time. Yeah. Yeah, that makes sense. And this will not happen for us in our case. We don't need to care about that. Because if we look at sort of this, you have 2 signals, the read and write signal, and they can never be high at the same time. You cannot read and write at the same time, so we don't need to worry about that. Okay, yeah, CAS latency. Okay, and this is interesting. So you could basically schedule a write to one bank and then continue to, for example, read from another bank. Yeah, I don't think we need to worry about that either. Okay, opening and closing rows take time. Okay. Okay. Honestly, this doesn't sound too hard. Maybe that is an interesting project as well, to write a simple SDRAM controller. Cool. Okay, but I think this basically confirms that this SDRAM will be good enough. We will be limited at this time cannot be lower than, say, 30 nanoseconds or something like that. But even if it is, so as I understand it, it works like this, that the idle state, sort of that ALE-L and ALE-H are both high. So we start looking from this point. And then suddenly the high signal goes low. That signals to us on the ROM side that we should sample the AD signals. And then the L goes low, which means that we should sample the AD signals again. And then we combine these two to build a full 32-bit word. And then the read signal goes low, but the Nintendo 64 will read it first when this goes high, as I understand it. And then when it goes low again, we get some time to prepare the next word. So there are like two critical times we need to care about, and it's this one, the time from that ALE-L goes low until the read signal goes low. And then there's this part here where after the first read, what is the time until the next read? But as I understand it, getting the next read after we have chosen a row, or what did they call it? Open a row. Like after we have opened a row, the subsequent reads should be faster. But yeah, I think this will be completely fine. So I think I'm gonna go with that. This one, the 64 megabyte SDRAM. All right, so back to the design. Right, here's just some random part. I don't think this one is there. Okay, so we just need to confirm the pinout on this one. So it's most likely not an issue, but it's always good to make sure. Where do they have it? I mean, they have this one. But where's the pinout? Okay, it's here in the beginning. T-sub. No, that is not the right one. Okay, this got a little bit complicated then. I'm gonna need to make a schematic symbol for this chip. I think. First of all, can we source it? Can we actually buy this chip? So let's check. Okay, DigiKey seems to have something. Mouser has a lot. That's good. That's good. that was the SRAM. Okay, but this looks promising. They have over 1,000 in stock. It's not cheap, but yeah, not prohibitively expensive either. All right, let's see if Farnell has it. And with 26 in stock. Okay. Well, it's not impossible to buy. That's good. Yeah, okay. So just get the feeling that there has to be a schematic symbol for something like this. Yeah, here's a similar one. 53, 54. Yeah, okay, so this one is correct. Just gonna have to check something. 1 second. So I had a different project a while ago. Here we go. Right, so for some reason Windows show up on the wrong screen. Anyway, here is a different board I made a while ago. Wow, time flies. And here I'm actually using SDRAM, and oh, wow, what happened? I just wanted to check the what happened here? Okay, I just want to check the pinout. Yeah, so it seems to be compatible as well. It's a 54 pin standard SDRAM. Yeah. Okay, that's perfect. So I should be able to just use the same. Yeah, that's nice. I think that, yeah, exactly. Actually, Goran, I borrowed your your fan out when I made that board. That was actually a while ago. But yeah, I basically took this this part from your board because yeah, routing that is sort of a pain. uh, yeah, so my idea here is to just sort of borrow that. I think this. Let's see here. Yeah, exactly. T-sub 54 book standard. But yeah, 2018. I still haven't really done anything interesting with this board. This was a let's see here. I put a USB 3 5-foot chip here, so you can transfer data to and forth the FPGA fast. And this is actually the first FPGA board I did, so it's quite messy and crappy, but it works. I even booted Linux on it. So yeah, I think I'm just gonna use the same footprint. All right. So yeah, let's remove the SRAM and just rename this. Yeah, I forgot all the fancy key combinations in KiCad. Remember, there's a button that can basically copy-paste the last line. Totally forgot what that was. Um, all right. Insert, okay. Unfortunately, that only works in one direction. Okay, too bad. Okay. I think all of these signals are just signals. There's nothing in between. No resistors, nothing. Just some caps. Yep. So I don't know how many caps you actually need, but I guess a few doesn't hurt. So just gonna copy. Yeah, maybe two. I have no idea. It's always kind of hard to know exactly how much you need. It will probably be fine. Okay, so now we have the SDRAM, the CIC chip. We're gonna need a footprint for that, or a connector. So yeah, you get the clock data and something else. Yeah, that's not a lot of signals. Okay, so now I'm gonna um, import the actual connector. Yeah, let's do that. So there we have that. So I'm gonna copy that. I'm gonna just do that outside here. 1 second. All right. Wrong project. Okay, let's see. Yeah, I'm a little bit rusty again. I need to import it here somewhere. Here we go. There we go. Nice. That saved us quite some time. So, of course, I will have the correct license and credit appropriately later on. But yeah, this is the connector from this board. So let's hook it up. Let's hook it up. So yeah, I guess I'll just do exactly what's done here. So kind of funny, the whole schematic symbol seems to be huge for some reason. I don't understand why. Ah, the thinker. Yeah, nice of you to stay this long. See you later. Well, still don't really understand why the hitbox for this symbol is so huge, but sure there is a reason. It always gets so messy. Yeah, it's kind of weird. I restart the program. It's as if the hitbox is like this big. Hmm. Well, never mind. Yeah, okay, so let's call this 1 second. That's kind of a nice feature in KiCad. If you create a symbol or a label with a number, you press insert, it will copy and paste it or create and iterate the index for you. Kind of nice. This is getting annoying for real. Like there's nothing. wonder what it is that it's hiding. This the symbol is not bigger than this. So strange. Hmm. Oh well, never mind. So if anyone in the chat knows what these left and right audio pins are for, I'm interested to know, because I've been looking up like information about the cartridge, and I don't know. Nobody seems to talk about these. Most seem to just not connect them anywhere. But are they the audio out signal from the game, or I don't know. I'm a little bit curious of breaking them out so that I at least can connect them somewhere. Right. Um, Now we have the pins. Now I just need to connect them somewhere. Okay, so going back here, yeah, right, we might want to have some 47 or low ohm resistors. Let's see here. I already have these, so I should be able to just copy this. So, how do we want to do this? I wonder if all of the signals need to go through the resistor network, because that's going to be a lot of resistors. Yeah. It seems like more or less all of the signals are going through resistors here. I guess that's fine. I wonder if you can lock schematic symbols. Maybe not. Well, this is extremely annoying. Like, the hitbox for the cartridge connector there. Yeah, it's almost like there is something over here that's invisible in the symbol. Yeah, now it's gone. I don't know what I deleted, but it was some speck of something. Well, it's gone now anyway, so that's good. That's a lot of resistor networks. Do I really want this? don't know. Can't really decide if I want the resistors or not. I mean, they don't seem to be strictly necessary, but I guess you could kill the FPGA if they're static and stuff like that. But yeah, resistors don't really help out with that either. Maybe a little. Mm. No, you know what? I'm gonna skip them. Okay. Okay, but that means that we have all the parts. We just need to wire everything together. And in order to know how we want to wire it together, so those left and right audio line connect to an undocumented custom chip on the motherboard. Oh, okay. That's suddenly more interesting. I will not remove them. Oh, now that you're here, Silan, I was thinking out loud about the series resistors. Like here's one card where they have series resistors for all of the external signals going into the FPGA. But there are other projects which just connect the signals straight into the FPGA. What do you think? Is it worth having them? Or do you think I should skip them? Because it's it gets a bit messy. Yeah, usually I put them, yeah. You're right, and I trust your judgment. Ah, damn it. Yeah, no, you're right. You're right. I should have them. Yeah, I just need to connect it all together. I mean, they are neatly aligned. Yeah, you're right. You're right. Like the way it's done here. Uh, hello? Yeah, it's not messy. It's basically just going through the resistor networks. Mm. Good point about the strength. Yeah, it would be annoying if the signals I transmit lead to glitches and stuff, or ringing and whatnot. I don't know. Yeah, good point. I'll add them. I mean, I already have the part in the project, and I have resistor networks at home, so should be fine. So I just need to pull them out here. I'll probably just do like this instead. Yeah, right. This order doesn't make sense either. It's going to be interleaved. Well, let's worry about that later. The precise order will change anyway. Oops. Oh, crap. Right, yeah, but let's worry about the details later. Okay, then we have the RAM. It will be connected as well. Yeah, okay. I think what's left now is to hook everything up, import the footprint or the layout of the outline here, the PCB outline. Get that in here, and then yeah, route the board. So before we do, like, it's gonna be super boring to watch, I'm sure. So, and there's not really gonna be any interesting discussions around that, I think. I think the interesting thing is basically the high-level overview. We've done that already. And we've placed all of the schematic symbols so that we have what we need. The rest I can do on my own, and it will be boring to watch. So thinking of ending the stream kind of soon. And then we can I can do another stream later on when it's more ready and more fun to watch, perhaps. So yeah, there you have it. And this is the board. I don't think I've missed anything. Like, if there is any component or connector or interface thing that I should add, then let me know now, because otherwise that's going to be annoying to add afterwards. So I'll have two SPI flashes, one for the FPGA and one for sort of boot up storage. And then we have the SD card, USB, UART, JTAG, 2P mods, the power stuff. Yeah, no, I think that is it. For the power, like we discussed before, we have V supply. Oh, right. Oof, this is going to be a little bit scary. I need a jumper here as well. So what I just realized was if you set the jumper to the 12 volt setting, you're feeding 12 volt to the V supply net, which is this net. But that is connected to the USB port, so it's going to blow up your computer. So that you shouldn't do that. So we should definitely have this as sort of yeah, exactly. Oops. So that's it's a bit of a dangerous design to have it like this. Like, I was just now thinking, should I have two jumpers? But then I am sure that people will end up doing it incorrectly anyway. Like, if I add a second jumper so that you disconnect this power line, Do you have a PDF of the schematic for a quick review? Yeah, I can. I'll make one right now. Plot. I'll post the link in the chat. 1 second. So yeah, that's something I will definitely fix now. That we don't feed 12 volts into the USB port. That is really bad. But other than that, I don't think there is anything that wrong in the schematic. Regarding this stuff, the configuration pins, here I have jumpers, so you can configure it as a master SPI and so on. I was thinking about removing this and hardwire it to master SPI only, because that's usually what you end up using anyway. So, and then there's this FPGA hold thing, which I don't think should be connected. Right, so this might be incorrectly wired, but I don't think so. So where's this connected? Nowhere. Okay. And this one? Okay. So I should remove this stuff. So Sylvan, if you're watching, I'll remove this R35 because it doesn't make sense anymore. This part. Never seen that whole pin used. No, so what I did in the previous board was that I was using slave serial mode, the 101 connection, because I wanted to try it out. And in order to do that, I needed to keep the flash in hold. It was a mess. It was a mess. So this time I want to make it easier. So do you also agree that master SPI only mode is the way to go? Like hardwire it to 010, because then we get rid of complexity basically. Yeah. Okay. Sounds good. Thanks for the review. That's really awesome. Um, yeah. Yeah, and I think these signals, they will just be raw signals straight into the FPGA. I might look at one of Greg's ECP5 designs with the micro SD card later on and hook it up like he's done. Like if he has some, don't forget you need 1.5K pull up for USB. Oh yeah, that is very true. That's good point. And I don't think I connect these anywhere because they were connected to the microcontroller. Yeah, okay, that's a good point. I'll add it to do here. And 22. Yeah. Good point. Should they be on? It was a while ago since I did USB stuff, but should they be on the connector side of the pull-up or on the other side? So it doesn't matter. Okay, perfect. I'll just do it like this. Cool. Yeah, and I don't connect the sideband stuff. Don't need that. But yeah, we're gonna have to find a good solution for the power stuff here. Because if I have a jumper here, I would also want to have a jumper here so I can disconnect this one. But having two jumpers makes it possible to have a dangerous combination. Yeah, but I mean, this board is for me, so yeah. Normally open. So I'm just gonna put this here in line. Mm. Cool. Yeah, anything else? I have some LEDs. Yeah, nothing special about that. UART, JTAG. I think that's basically it. Why isn't that pin just connected to VBus? Yeah, so the danger is if you have 12 volt. Or do you mean the freed bed? What I meant before was that if you set the jumper to the 12 volt mode, so here, then you feed 12 volt to V supply. V supply is this net over here. So then you would feed 12 volt to the V bus straight into your computer. That's what that is about. The other side of the FP1. Oh, you mean you want to have the jumper on this side instead? It should be V bus. Okay, okay. I'm a little bit confused. Do you mean that I should move the jumper, or that the names are just remove the jumper you just added? Okay. And then connect FB1 to. Okay. You mean. Okay. To the right. Okay, okay, okay. So I'm just gonna. So you mean like this? Connect FB1 to just VBus. Okay. Sorry, this is the whole delay stuff is also making it really annoying. Let me just remove. So, right, here we have the V supply. Let me just move this again. So, this is how we had it before. Just wire J1, which is, where do I have J1? I'm getting, right, okay. We can remove this then. So, so now we have the ferrite bed or bead. Then the other pin of FP1 to VBus. Okay. Right? Oh. Right. I don't know why I didn't think about this. It looks extremely simple now. And then I wonder if you can make this in a nicer way. I guess if I rotate it, because this is what you mean, right? Because now we have the VBus, and that's it. And there won't be any backfeeding. No worries about it. Yeah, perfect. So I guess if I now rotate this, and then we can just swap those. Do like this. Then do like this. It's a little bit cramped, but you get the idea. Does this make sense? Looks good to me. Perfect. Thank you. I think I'm getting tired because I didn't realize the simple logic right now. But yeah, so I think that's a perfect end of the stream now. So thanks again for the review and your patience with me. So yeah, I'm gonna wire this up, and I guess tomorrow perhaps I'll make another stream, or we'll see. Hopefully I'm gonna be able to finish this quite quickly. Stupid question, but the ferrite bed is to filter high frequency noise. Well, yeah, more or less. Usually you want to filter the voltage coming from USB supply. It can be anything on this side. Yeah. All right. If anyone has any more question, go ahead, just ask. Otherwise, I'm gonna be shutting it down now. So yeah, thanks again for watching and hanging out. It's been fun. And yeah, see you again next time. Thanks, you too. All right, see you around.